So imagine that you're the engineer responsible for actually introducing this particular nasty vulnerability in your code base. I'm Filipe, and today I'm going to show you two static analysis tools that actually will probably prevent some of these vulnerabilities to show up in your code. So I'm actually a cryptographer at Trilobits, and I really like programming languages. And for those that don't know, Trilobits, we're a software security research and development firm. And besides doing research in program analysis and engineering, we also have an assurance practice, which has a blockchain team. We have an application security team, and we also have the cryptography team, where I'm actually a part of. And you probably have heard of some of these tools like Slither and Echidna. And today I'm going to present you two other tools that you could use in these particular code bases. So as an overview of today's talk, we're going to talk about these zero-knowledge programming languages. And before that, we're actually going to show you what zero-knowledge proofs and these languages are. And the languages that we're going to talk about and the static analyzers are going to be Cairo and circum. And just to get a sense of the room, who has actually heard or programmed in Cairo or circum before? All right, quite a few people actually. So what are zero-knowledge proofs, and what are these languages? So zero-knowledge proofs allow you to actually prove facts about the execution of programs. So I can actually, for instance, prove that I know some secret input to this program that makes the program output some value output. And this proof, then I can give it to you, and you can actually verify that I was being honest, and I actually know the secret input that makes this program output this value. And in a way, this makes it if you need to verify some computation in your application, this makes it a very scalable solution. So you actually don't need to recompute the program. You just need to verify the proof. And this is a very simple and efficient task to do. So the problem here now is that to be able to generate these proofs, these programs need to be actually encoded in, let's say, mathematical magic, some constraints and some polynomials. And to help you actually do this, we have these zero-knowledge programming languages. And you can see some examples of these languages on the right-hand side. We have some more basic ones like circum and libsnarks, which basically make you write the circuits by hand. And then they provide you a way to compile these circuits into the constraints themselves. But now we're seeing some more high-level programming languages, which actually allow you to program in a natural way like you used to program, let's say, in Python or JavaScript. So we get to this place where we have this new programming paradigm. The languages are very young, and most of them are a lot of design quirks. And at the same time, there are very few developer tools, basically only syntax highlighting. And this makes it so that development in these languages is very hard, and testing even harder, so you can't really be sure about the code you're writing. And as auditors at Trilobits, we also need tools to make our audits easier and find more bugs. So we need tools that help us highlight potential vulnerable pieces of code, and also to perform variant analysis, which is when we actually manually find a bug, we want to make sure that all the rest of the code base is free from this bug. So for this, we need tools. And there are no tools for the languages. But still, despite this, these languages are actually being used to power a lot of services that handle millions and millions of dollars. So there's two examples here, DYDX and Tornado Cache. And DYDX is powered by Cairo, and Tornado Cache, recently on the news, is powered by circum. And these are actually the two languages that we actually are building static analysis tools for. And you can see here in the example, I hope it's readable, but this was a bug in Tornado Cash a couple of years back, where the developer actually used the wrong type of assignment. So instead of using a less than equals symbol, he used just an equal symbol. And this is the difference between actually enforcing a constraint on the system and not enforcing the constraint. And it would make it so that you could forge a proof and steal funds, basically. This is a reasonable mistake to make, since the language is not that easy to use for someone coming from a different language. And that's why we need tools to prevent this type of mistakes. So I'm going to start by presenting the static analyzer for Cairo programs. But since a lot of people also don't know about Cairo, I'm going to show you just a simple example. And I hope you can read it fine. But on the left-hand side, we have a library Cairo file. And you can get a sense of the language. So we have function definitions. We can assign variables and function calls. And we also have an assert. So on the first function, you check that the caller and the owner is exactly the same. And then we have a mint internal function, which will increase the balance by some amount of tokens. And then the developer was actually kind enough to introduce this third function, which is the test mint function. He just used it to test. On the right-hand side, we have the actual interface of the contract. And there, we import from this library the two mint internal and assert owner function. And then we have the external function, the mint function, which will check that the owner is the same as the caller. And then we'll call the mint internal function. So can anyone actually find a bug or an issue in this code base? Yes. Yes, exactly. So Joran knows a lot about Cairo as well. So if you look here, this import statement, mint internal and assert owner, it's importing these two functions, right? But actually, this import statement also imports this test function because of this particular decorator here. And it would make it so that this function is actually exposed in the contract, and you could call it directly. This is not obvious at all for someone that's coming from a regular programming language where imports only import what you're trying to import. And because of this, we actually need tools to show you that there's these bugs. So this is one of the vulnerabilities that Amarna finds. And so far, we have implemented 14 detectors. This implicit function import is detector number 12. But we also have more code quality and informational findings, like unused arguments in functions or imports that are never used that you can find. The compiler, we used exactly the same parser as the Cairo compiler, so we view the code exactly as the Cairo compiler would view it. And this allows us to, since the tool is ours and we have the knowledge of how to use it, we can actually easily write rules targeting a particular code base. Let's say I'm auditing a Cairo code base and I find this particular pattern. I want to find the pattern repeated across the code base. And the tool is also open source. You can go check it out and try it in your project if you want. There's also an Amarna action, so a GitHub action called Amarna action. You can add it to your GitHub pipeline, and every time you push to the repo, you'll get some warnings on GitHub directly with this serif view, showing that there's some new vulnerabilities being introduced. And also, it's very easy to use. You can just pip install it and run it in your code base. There's also a serif export. So serif is the standard file format to view static analysis results. And you can easily visualize them in VS Code. So if here you have this function which has this variable A that's not used for anything, and you'd get this message saying that you can remove this variable, it's not needed. So we plan to soon also build the VS Code native extension. So as you write your Cairo code, you get the findings straight away and directly in VS Code instead of having to run this tool by hand. And we also plan to introduce SSA and data flow analysis that would enable us to write more complex rules and also decrease the number of false positives that some of the rules still have. And this is the static analysis tool that we've been building for Cairo programs. But some of these problems and vulnerabilities happen pretty much in any language. And that's why we're starting also this new static analysis tool for the circum language. And this is called circumspect. So circum is a circuit compiler language, and it's much more low level than Cairo. So if you look on the right-hand side, you have this example of a circum program that actually ensures that the product of two numbers is the output of the program. And you cannot write much complex code, but still, as you saw with the tornado cache bug, there's still a lot of problems that could arise in this language by using this constraint enforcing. The language will just output these R1 CS constraints. These are actually what's used in a different tool to prove assertions about your program. And just like Cairo, there's very few tools for circum, besides the compiler, obviously. And our tool is also written in Rust, just like the circum compiler, and we also use the circum parser to actually load the code, etc. Then we also have an intermediate representation already with SSA, which allow us to do some basic data flow analysis. And so far, we have about 6 or 7 detectors. And the tool is not yet available, but it will be soon available in the next couple weeks. On the right-hand side, we actually see this very large program, but the interesting part is here at the end, where these L-out and E2 variables are actually never used in a constraint enforcement. And this will also be caught by the circumspect, because it will find that these variables are never used in a constraint. And this is because the constraint here at the end uses N-out instead of using L-out variable. So, yeah. And currently, we are focusing on finding issues that are not found by the compiler. But if you actually use circum, I recommend you to always use this -- inspect flag. Otherwise, the compiler will not tell you about some issues that you might have in your code. And just like Amarna, circumspect can actually output results to the SARI file format, which then you can use in your GitHub integration or just to view it in VS Code. And if you have a look here, this is actually the result of running circumspect on the previous snippet of code. And you see here that the value assigned to L-out is not used in a witness or a constraint generation. And this would tell you that there's something wrong with the code. I need to check what's going on. And now I have a mission for you, which is actually to go and try Amarna. So just download it or pip install it, and circumspect, you can expect it soon in the next couple weeks. Thank you for your time.